Radioactivity is natural. It's a natural part of the environment. It's not something that we have done to the planet. It's always been here. Our bodies are accustomed to it and have developed methods of dealing with natural levels of radiation. We also have small amounts of radiation that penetrate through our atmosphere from outer space. The ground contains radioactive atoms. In some parts of the country, there are significant amounts of radon in the soil that emit radiation. Any element above atomic number 83 is unstable. That's bismuth. And all of those are going to be radioactive. Some of the isotopes of elements that are below that are also radioactive. So it's just naturally here. So this decay, it happens at different rates for different types of nuclides or radioactive isotopes. Some decay very, very quickly. Others decay incredibly slowly. So the quantifying thing for that is called half-life. Half-life is how long it takes for half of the parent nuclides in that sample to decay to the daughter nuclides. So for half of the sample to decay, that's the half-life. So after one half-life, you have half as much of that original material. Another half-life cuts it in half again. So this is a little deceptive because you might think, well, 2 half-lives and it's all gone. No, it's cut in half every time. And so the change gets smaller and smaller each time. You can't add 2 half-lives together to get a whole life. So after 2 half-lives, you've got 1/4 of your sample. After 3 half-lives, you've got 1/8. After 4, you'd have 1/16. It just gets cut in half. So something that decays quickly has a short half-life. Things that decay slowly have long half-lives. So a decay event is one nucleus undergoing radioactive decay. That's an event. So something with a short half-life is going to have a lot of events in a particular period of time. Something that decays slowly may only have one decay event every year. It can be very, very slowly. So some things have half-lives of billions of years. Radon 220 has a half-life of approximately 1 minute. So if you started with 1 million radon 220 atoms, after 1 minute you'd have 500,000. After 2 minutes you'd have 250,000. After 3, you'd have 1/8 of a million, okay? So the radon decays, I'm puzzled by this. Radon 220 atoms, and all of a sudden it's thorium 232 atoms. I don't know what's going on with that. I think there's a mistake there. Thorium 220 is another radioactive element. It's got the same mass number, but it's much less active. It decays much more slowly. Yeah, I think that's another typo. Good grief. I have to review this. Because here's thorium 220, and now all of a sudden we're talking about thorium 232. Just try to let that go, and I'll try to let it go and fix it for later. Here is a visual graph of what's going on with decay. So here's the number of atoms in millions. So starting with 1 million. This one has a half-life of 14 billion years. After 14 billion years, half of it has decomposed. Does it have very many decay events per year? Not very many. No. So after 1 billion years, you'll have 500 million of these left. 14 billion. After 28 billion years, you're going to have 250,000. So you get the idea? So the decay is a curve, and it just trails off and gets smaller and smaller and smaller until eventually you get down to one atom, and that would decay. But that's going to take a really long time. Each half-life has its own unique, each radioactive nuclide has its own half-life. Good grief. Maybe need to take a break. Half-life is not affected by physical conditions, the environment. You can't put this in a freezer and cause it to decay more slowly. You can't heat it up and cause it to decay more quickly, put it in a vacuum. It just decays because this is something that comes from the nucleus being unstable and falling apart. And nothing you do on the outside is going to affect it. So each different isotope has its own half-life and its own type of decay. And so this is just for your information. Do not memorize this. Thorium-232, 14 billion years. That undergoes alpha decay. Uranium-238 also does alpha decay. That would be 4.5 billion years. Carbon-14, 5,730 years. So after 5,730 years, half of it's not carbon-14 anymore. Radon-220, just under a minute. Thorium-219, 1 times 10 to the minus 6 seconds. That's a millisecond. No, a microsecond. A microsecond. Okay. So half-life can vary tremendously, from microseconds to billions of years. So we need to know how to do very simple half-life problems. There are fancier ways to do this using exponents and stuff. We're not going to do that. We're just going to take things and cut them in half and count how many times we cut it in half. Okay? If you want to do the other way, fine. So a radium-226 sample initially contained 0.112 moles. How much radium-226 is left in the sample after 6,400 years? The half-life is 1,600 years. So we've got 0.112 moles of this. There's our lump. And it's asking how much is going to be left after 6,400 years. So one way you can approach this is you can say, well, how many times does 16 go into 6,400? 6,400 divided by 1,600, 8 over 4? Yeah. Use your calculator. So 4 half-lives. So I'm going to cut this in half 4 times. If you don't think to do that, that's okay. So here's 1,600 years. After 1,600 years, this gets cut in half. Personally, I don't trust my brain to do this. You've got a calculator, might as well get the number right. 0.056 moles. Well, that's not 6,400 years. So another 1,600. So we divide that by 2 again. 0.028 moles. So we're up to a total here of 3,200 years. So we need to keep going. Another 1,600. Cut that in half again. 0.014. So now we've reached 32 48, yeah, 4,800 years total time. So cut it in half again. 0.007 moles. And 4,800 plus 1,600, that gives us our 6,400. So it's kind of like a first grader way of doing it. But this is the level that we need to do it. And so this is what makes sense if you have the basic understanding that we want you to have. This is all you have to do. That's all it's asking. Yeah. It does not matter if it's given in moles, kilograms, grams, just the quantity. It gets cut in half. If it gave you the initial conditions in moles and asked you for grams, I can't imagine doing that to a student, but we could. You could figure out how many moles are left and then convert to grams, or you could convert to grams first and then do the cutting in half. It won't necessarily give you moles. It might give you a mass, and then you just cut the mass in half. It's always about cutting in half. How many times did you cut it in half? Any other questions? Let's take a break and we'll come back to this.